A related rate problem is a problem in which you're looking for how one variable changes with respect to time. So everything that we do with related rate problems will be done with respect to time. So any derivatives we take, they won't be with respect to x, they'll be with respect to t, even if there are no t variables in the equation. And generally, there will be no t variables in the equation. We'll be differentiating x's and y's and thetas and whatever else is with respect to t. So all of our derivatives for related rate problems will be done implicitly. So we're going to say, all right, suppose this thing is happening and this other thing is happening. And based on that, how fast does this car travel at this exact instant? And that's what a related rate is. There's some other situation. There's a couple different situations going on, something going on. Something's moving a certain speed in a certain direction. How does that affect this other thing? That's what we're going to be looking at. It sounds a little weird maybe and a little complicated, but it's not. So there's a few important steps that you'll need to take. First, read and understand whatever problem you are working on. Figure out what variable's rate of change you're looking for. So you're always going to be looking at some variable's rate of change. So you'll draw a picture and label the important things on your picture. And as you draw and label your picture, it's very, very, very important that you do not label any values that are changing. So if I say that a car is driving at 20 miles an hour and that at some certain time it's 5 miles away from somewhere, okay, you can't label the distance as 5 because that distance is changing. At some particular instant, it's 5, but the car is moving at a rate of 20 miles an hour, so that distance is changing. Okay? Only label constants. So if I say, suppose I'm standing here and there's some other, there's an animal here and it's walking this direction, okay? And I say that I was 10 feet away from this bear or something, and it was afraid of me and started running away. This 10 feet that I was away from the bear, that never changed. This distance between me and the starting point of the bear didn't change. Okay? The distance between me and the bear is changing, right? And the bear is moving at a certain speed. We might be able to, we wouldn't be able to label this distance because this distance is changing. We couldn't label this distance because it's changing. We couldn't label the angle because the angle is changing, but we could label the 10 because that bear was 10 feet away from me when it decided that it was afraid of me. Good or no? And the reason why we don't do that is it's to help us to not plug in any changing values into whatever equation that we write, which is step 3, writing an equation, before we take the derivative. So we're going to take the derivative with respect to time to freeze the situation that we're looking at an instant in time. And when we freeze it at that instant in time, that's when we can plug in all of the other information that's given to us. So we'll read the problem, we'll draw a picture, we'll label the constants, and we can label, I could label this as a theta, or I could label this as a z, or I could label this as a q, or whatever, right? I could label things that are changing with variables, but I can't label them with numbers. Okay, we'll write our equation that relates all our variables together, and then we'll differentiate with respect to time and plug in all the stuff that was given to us initially. Does that sort of make sense?
Yeah.
All right, let's do one of these because then it's going to make more sense. So we have a hot air balloon that is rising straight up from a level field, and I am tracking it from a distance of 500 feet from its liftoff point. Blah, 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 blah. Some more words that you can read on your own. I'll give you a second to do that, and then we're going to draw a picture. Are we ready to draw our picture? Yeah? Ready to draw a picture?
Yes.
All right. So here is a hot air balloon rising up. There's the balloon. Okay. This is its starting location. And here I am over here tracking that balloon. I'm tracking that balloon from a distance of how much?
500 feet.
500 feet. Is this 500 feet changing, or is it the same no matter what?
It's the same.
It's the same, so I can label that 500. All right. Everybody good so far with that?
Yes.
Okay. Now, we're also given some other information. So we're given information that the angle that we're interested in is a theta equals pi over 4 radians. Well, first of all, I don't even have an angle on here right now. It's talking about the angle of elevation from the tracker to the balloon. So that's this angle right here. Is pi over 4 changing?
Yes.
Yes, it's changing. So I'm not going to label it as pi over 4. I'm just going to label it as theta for right now. Everybody good with that? Good or no?
Yes, good.
Okay. How is theta changing? What is the rate of change of theta with respect to time? D theta dt. What is that value?
Plus 0.14 radians per minute.
That's 0.14 radians per minute, right? It's changing at 0.14 radians per minute. In fact, it's increasing at 0.14 radians per minute. Okay? We want to know how fast is the balloon rising. So that would be a change in this distance with respect to time. Let's call that distance y, and say that we are looking for the change in y with respect to time, or dy dt. Everybody good with that or no? That's what we're looking for. Are we given a y value at all?
No.
No. But this should all be enough for us here. So we now need to figure out some way to relate theta, 500, and the y together in one equation. So anybody got an equation we can use for that? How are these three things related?
Could you do tangent theta is equal to y over 500, or y is equal to tangent theta times 500?
Yep, exactly. Tangent theta is opposite over adjacent, or if we want to just solve for y, y equals 500 tangent theta. Everybody agree that that is just a little bit of right triangle trig that we can use to write an equation that relates them?
Yes.
Okay. So now what we're going to do is we're going to freeze this at an instant by taking the derivative with respect to time. So what's the derivative of y with respect to t? Just like the derivative of y with respect to x is dy dx, the derivative of y with respect to t ought to be dy dt. And what about the derivative of 500 tangent theta? That ought to be 500
Secant squared theta.
secant squared theta. And we're taking the derivative of a theta term with respect to t. So we should attach to that a d theta dt. Any variable that I take the derivative of in here, unless it happens to be a t, will always get a dy dt or a d theta dt or a dx dt or a dz dt attached to it. Okay. Everybody good with that?
Yes.
All right. And we want dy dt. So dy dt ought to equal 500 times the secant squared of what's our theta value that we're freezing this at?
Pi over 4.
Okay. And our d theta dt value is 0.14. What's the secant of pi over 4?
Two over root 2.
2 over root 2, which is the same as just root 2, right?
Yeah.
Yeah, and so if we square that, what's root 2 squared? It's just 2. So 500 times 2 times 0.14, which gives us what, 1,000 times 0.14, or 140 feet per minute. So that's how fast the balloon is rising at that exact instant in time. Good or no?
Good.
All right. We're going to do a couple more of these. So I'm going to let you guys take a minute or two and read that one and see if you can draw the picture to set this one up. And then we'll go through and make sure you got it all labeled correctly. So I'll give you 2 or 3 minutes to read and draw. Ready? Go. All right, you guys got a picture of this one? Got stuff labeled as best you can?
Sort of.
Sort of, okay. So first off, we got a police car. It's approaching a right-angled intersection from the north. So there it is. And there's my intersection, right-angled. Okay. We've got another car that's turned the corner moving east. So that's why I've drawn this going to the right here, going east. We know that when the police car is 0.6 miles north of the intersection, the speeding car is 0.8 miles to the east. Are those distances changing if the cars are both moving?
Yes.
Yes. We also know that the distance between the two cars is increasing at 20 miles an hour. So that'd be the hypotenuse of this right triangle. And that's also changing, true? So is anything in this problem not changing besides this right angle?
The speed of the police car?
Okay, the speed of the police car, right? But that's not a physical thing that I can draw on here, is it?
Nah.
Nah, it's not a physical quantity that could be, labeled on this graph. So I just got to come up with the variables for all these, just out of habit. I'm going to call the horizontal one x, the vertical one y, and the hypotenuse z. Everybody good with that? How are these three variables related?
The Pythagorean theorem.
Yep. X squared plus y squared equals z squared. Exactly. So now let's list out all the things that we know. We know that at the moment that we're interested in, the police car is 0.6 miles north, so that'd be y equals 0.6. And at the distance, or at the time we're interested in, the distance away from the speeding car is 0.8, so that'd be x equals 0.8. We don't happen to have the z value. We could figure it out, though, if we need it later on. And then we're interested in how fast x is going, right? How fast x is changing. So that would be dx dt is what we're looking for. What about dy dt? Do we have that? How fast this distance is changing?
60 miles per hour.
It's 60 miles an hour. Now, is y increasing or is y decreasing?
Decreasing.
It's decreasing. Therefore, its rate of change has to be negative. So anytime you have a quantity that's decreasing in a related rate problem, its rate of change has to be negative. Okay? And then do we have a dz dt value? How is z changing? Z is changing at 20 miles an hour. In fact, it's increasing, so that one's definitely going to be positive. So we've got everything listed, I think. All we need to do now is take our derivative. So 2x, and then since it's with respect to time, dx dt, plus 2y dy dt equals 2z dz dt. Everybody good with that? Good or no?
Yep.
Okay. So we've got the x. We're looking for dx dt. We've got the y. We have dy dt. We have dz dt, but we're missing z. So how do we find z at the instant we're interested in? Just use our Pythagorean theorem. 0.68 squared plus 0.6 squared plus 0.8 squared equals z squared. And what does that give you for z? Z should equal
1.
1. So now we have x, y, and z to plug in. We've got dy dt and dz dt to plug in. We just need to plug them in and find dx dt. So 2 times 0.8 dx dt plus 2 times 0.6 dy dt equals 2 times z times dz dt gives us 1.6 dx dt minus, what is that, 1.2 times 60, that's 72, equals 40, or dx dt equals 112 over 1.6, which, what does that come out to be? 70, I think? 70 miles an hour? Good or no? Any questions there? Any issues with that? All right. Everyone's good. Let's do another one then. We got one more of these we're going to do, and then I'm going to give you guys some time to practice on optimization and also practice on some of these related rates because I posted up an assignment for that. So, everyone good? Let's do this one. Take a minute and see if you can come up with a picture and label it as best you can. Everybody feel like they got a good picture there?
Yeah.
All right. So we've got a cone that's getting filled up with water, standing with the point down. Now this cone has a height of 10 feet. Is the height of the actual cone itself changing or no?
No.
No. So from here to here, that wasn't very good. That's 10 feet, and that's not changing. What about the radius? Is the radius of the cone changing? No. Cone isn't changing itself. What we're doing is we're filling the cone with water up to a certain level, right? And the height of that is changing, and the radius of that is changing, right? But the height and the radius of the actual cone are not. Everybody agree with that?
Yeah.
All right. So first off, what are we looking for? We want to know how fast the water level is rising. So that's a change with respect to time of that height. We're looking for dH/dt. And we're looking for dH/dt when h is 6. Yeah? Everybody agree there?
Yeah.
Okay. So, well, what else are we given? That water is flowing in at this rate, 9 cubic feet per minute. What is that?
The change in volume of the cone?
Yep, it's the change in volume, not necessarily of the, I mean, it's of the cone of water as it fills it, not the actual cone itself, but the cone that is formed from the water. Yep, that's volume, and we can be clued in by the units, cubic feet per minute, right? So that's 9. So what equation can we write to relate the volume and the height of this thing? It might have to include a radius also.
1/3 pi r squared h.
Yep, volume equals 1/3 pi r squared h. And the problem with that is it's got an r and an h. So we're going to have to find a way to relate r and h together so that we can replace, hopefully we can replace the r in terms of h's, because we're looking for dh dt and we're given a height. So how are we going to relate r and h to each other?
Pythagorean. With that.
So Pythagorean theorem is going to have to give us this one also. Do we know anything about this slant height of the cone?
No.
Nah, so that's going to be a little bit more difficult. All I really know is that this is a right angle and this is a right angle. And with any luck, that should clue us in.
Similar triangles?
Similar triangles, right? Because they share this angle down here in the bottom. And so an angle and another angle that are congruent proves triangle similarity, angle, angle. So that tells us that the ratio of the radius to the height, 5 to 10, is equal to the ratio of the radius to the height of our cone of water as it fills up. So what does r equal? R is equal to 5h over 10 or just h over 2. Everybody good with that? Agree with that?
Yes.
So now we've got 1/3 pi times h over 2 squared times h, or pi h cubed over 12 is our volume. And now it's all in terms of h. What should we do next?
Take the derivative?
Take the derivative with respect to t. So dv dt equals, the derivative of this is 3 pi h squared over 12, or just pi h squared over 4, and then times dh dt. We want to know dh dt, and we have dv dt and we have h, so we just plug them in. 9 equals pi times 6 squared over 4 dh dt. And if you solve that out, what does dh dt become? 4 times 9 is 36. Divided by that 36 is a 1. So 1 over pi feet per minute. Any questions on that? Or is that good?